Hey everyone, can you all hear me okay? Great, awesome. So I normally like to start talks off with a question. So the question I thought I'd ask today is just to see how many people here own and actively use an Android device. So I know I do. Okay, so that's a good 90% of the room, if that. So all the techniques that we talk about today, all the attestation techniques, the root detection techniques, have probably been used on 90% of your devices within the past 24 hours, let's say, either with or without you knowing. And we'll go into detail on what that means in a minute. So what are we actually going to talk about today? Well, I've broken it down to three main areas, but primarily we're going to be talking about Android attestation, Android tamper detection, right? How blue teamers or how software engineers protect Android applications. I've broken it down into three main areas, and primarily those are three different examples. The first example we're going to look at is a window into the world of Android attestation. This is an open source tool I've created, which is basically going to set the scene for the later demonstrations. We're then going to look at a fairly popular Android game, and we're going to have a look at how they implement root detection. And then finally, we're going to look at things at a much grander scale, right? We're going to have a look at how organizations like Google and Huawei implement attestation on Android devices. First things first, though, who actually am I? My name is James Stevenson, and around about 6 years ago now, I entered the computer security field. I've been in roles from software engineering to penetration testing and vulnerability research. I've also released a few books on similar topics, and I occasionally talk at conferences like this. But that's enough about me. Let's jump into Android attestation. So what is Android attestation, right? That's what this talk is about, but what actually is it? As I said, it's about software engineers, application developers having assurance that their applications are secure. And we can generally break that down into three main pillars. We have device integrity, application integrity, and user integrity. The first pillar we have is about having an unmodified Android application, right? As a software engineer, we want to ensure that our Android application hasn't been modified or tampered with in some way, hasn't been patched or hooked or anything to that extent. As an example, maybe we're a game developer, right? We want to ensure that our Android application, our game, someone hasn't added 1,000 points or score, whatever the case may be. The next pillar we have is about having integrity on our device. We want to ensure that the application our device is running on is legitimate, that it's not rooted or tampered with or compromised in some way. A good example of this is as a bank, right? If we create a banking application, we want to make sure that our application is running on a non-compromised device so that our users don't become compromised in turn. And then finally, about user integrity, right? We want to ensure that who is using our device is an actual human being. We want to make sure that machines aren't using it. Examples of this are things like bot farms and things like that. And we're going to be focusing on those top two today, device and application integrity. So let's have a look at some examples. Right? So here we have 4 Android applications all running on a rooted Android device. And all of these applications have rightly so detected that they're running on that rooted device. Right? They all have a little pop-up that says, hey, this device is rooted. I'm going to limit functionality to you in one way or another. And we'll see this a lot in banking applications, applications that deal with financial transactions, or streaming services, things like that. And they'll do this for a few reasons. Maybe they're looking to protect the user, maybe they're looking to protect intellectual property, or things like APIs, things like that. So let's have a look at another example. We're going to run the same application on 2 different devices. The first device is standard, normal Android device, and the second device, a rooted Android device. This application is basically a wrapper around Google Play services. We don't need to know what that does for now. We just need to know that the application is going to detect if the device is rooted or not. So running that application on the first device. We run it, and it comes back as passed. Great. Exactly what we would expect, right? Normal Android device passes the checks. So now let's run that same application on a rooted Android device. Okay, that comes back as failed. Again, exactly what we'd expect. Normal device passes checks, rooted device fails checks. But how does that application know that the first device was legitimate and the second device was rooted? Well, there's a few different techniques that could be at play. As I said, that application was using something called Google Play Safety Net, basically a system component on your Android device. And also, app developers can do proprietary means, right? They could write their own code. They could use a third-party library to do that sort of root and tamper detection. So we're going to cover all three of these areas today with each of our three examples. And as I said, the first example we're going to look at is a tool called Runic. Now, Runic is an open source tool I've created, available online. You can go find it. And it's basically, for us, it's going to be a window into the world of Android attestation. The techniques, the variables, things that we look at today, are going to start cropping up in our other examples. The way Runic works is we have a little Android application running on our device. That reaches out to a server, and it gets back a confidence score. We can kind of see it in a little pop-up that should show up. There you go. And that confidence score is between 0 and 100. 0 being no integrity, and 100 being complete integrity. And that integrity is relating to both the device and the application. So how does that work? Well, as I said, we have our device, we have our application, and we have our server. Every so often, that application is going to reach out to that server, and it's going to send a bunch of data, and we'll cover that in a second. That server then does a handful of computation, including using some machine learning models, and then it sends that confidence back to the device, back to the application. So what data is used in that computation? Well, we can see some of it here. We don't need to read everything on the screen. It's just to give an example. We can see things like the application signature, if ADB is enabled, the boot state, patch level, things like that. And then on the server side, we can see things like looking at the emulation state, looking at some signatures, permissions, things like that. And again, all of that wraps into getting this integrity score back to the device. So looking at Runic, as I said, it's kind of a window into the world of Android attestation. We're going to have a look at some in-the-wild examples now, and we should start seeing a lot of these techniques cropping up as we go through. So the first example we're going to look at is the Among Us Android application. Insanely popular game, insanely popular Android game, and we're going to have a look at how tamper detection and root detection is done in this application. So we're going to use a tool created, again, open source, called Disintegrity. And Disintegrity is going to take that Android application, decompile it, and have a look for entry points of root detection and tamper detection checks in place. And from that, we get this little HTML output. We can see a class here called rootchecker.smiley. So we're going to decompile the code, have a look at what that is doing, and we can see a library called sentry.io. Okay, well, we can go to their website, we can have a look at the docs, and with all of that together, we can build a picture on the types of root detection checks that Among Us is using. And I've broken this down into 4 main areas to give us an idea of what's happening. So the first check they're doing is they're looking for the keys that have been used to sign the kernel on the device, and they're checking to see if they're test keys. Next, they're looking at the file system, and they're saying, okay, well, what files exist on the device, and are they related to rooting in one way or another? Next, they're checking to see if the SU user exists. And finally, they're checking to see if any rooted packages exist on the device. All things considered, some fairly preliminary techniques to identify if the device is rooted or not. I'd fully expect Among Us to have additional anti-cheat mechanisms, just not when it comes to root detection. So if that's how a fairly popular Android game is performing root detection on a device, what about root detection and attestation at a much grander scale? So let's have a look at how Google Play Services and Huawei App Gallery are doing this kind of attestation with 90% of the people's here devices. Well, 2 very similar names, right? Google Play Services Safety Net and Huawei Safety Detect. But all things considered, very similar features. So where there's a feature in one, there's a parallel feature in the other. And each of these are basically APIs that developers who create applications can call to check one thing or another. The first one we have is about device integrity. So this is where a developer can call that API and identify if a device is rooted or not. Then we have the URL analysis API, which can be called to check if a URL is known to be malicious. The captures API, which can be used to identify if the user is a human or a machine. And then finally, a really interesting one, which is the app analysis API, which will allow a developer to identify if there's any known malware on the same device as their application. So you can probably guess we're focusing on that top one today. We're focusing on device attestation and device integrity. And we're going to be specifically focusing on Google Play Safety Net. So as I said right at the start, right, 90% of people here have Android devices, and you probably have Google Play Services or Huawei App Gallery. And that's where these attestation checks start. So in the case of Google Play services, that will periodically run, and it will download an snet.jar file. Now, that snet.jar file depends on the version of Google Play services, and it depends on the version of your device. But primarily, it's going to do the same thing. It's going to aggregate a whole amount of information from your device and send it over to a Google server. That Google server is then responsible for doing an amount of computation. Potentially it uses some machine learning models or things like that. And then third-party developers on the same device can call that API that we mentioned and get back a handful of variables, including a CTS profile match and a basic integrity. And that will give them an idea on if the device is rooted or not. So that server is closed off, right? We have no idea what happens on that server. We can assume that it's some sort of machine learning model. But what we can look at is these snet.jar files that get downloaded onto our device. So that's what we're going to have a look at now. We're going to have a look at one of these snet.jar files. It's from around about 2020 or so, and we're going to have a look at what's actually happening in there. So each of these snet.jar files is broken down into modules. Each of those modules are responsible for aggregating a different type of data from the Android device. So the first module we're going to look at is probably the most representative for identifying if a device is rooted. It grabs things like the verifying boot state, verifying mode, security patch level, and if OEM unlock is supported. So when we look at this information, which again is being sent over to that Google server, we might say, yeah, that makes sense, right? If we're looking at identifying if a device is rooted or not, those variables make sense. So let's jump on to another module, which is a bit more left field. So this is the settings finder module, and it grabs things like if ADB is enabled, the fingerprint status, the lock screen timeout, lock screen type, things like if non-market apps are enabled, and things along those lines. And as I said, it's a bit more left field, right? If we were to look at these variables, we wouldn't necessarily say, well, the device is rooted or not. Just because ADB is enabled or just because non-market apps are enabled doesn't mean one way or another if a device is rooted. And this probably hints at that Google is using some sort of large machine learning model for this computation and for this analysis. Because at the one-off scale, this information probably doesn't hint at a device being rooted or not. But on the scale of data that they have access to, you can start to build those patterns. So the next module we're going to look at is probably my favorite module. This is the SD card analyzer module. What this module does is it saves an image to the external storage of the device. It waits some time, and then it goes back to that image. And then if that image has been changed or altered in some way, it flags it, takes a hash of it, and sends it over to the server. This is probably for some anti-tampering, anti-emulation, anti-malware technique, and it's a really interesting one. Next, we have the routing file finder. This is very similar to the Among Us application that we saw earlier on. Basically, it just has a list of files related to routing techniques, and if they exist on the device, it takes a hash of them, sends them over to the server. Next, we have the preferred package finder, so very similar to Windows. On Android, you have preferred packages for things like your browser or your app store. And in this case, it takes a snapshot of what those are on the device and sends them over to the server. The final module that we're going to look at today is the captive portal detector. Again, a fairly simple one. What this does is it reaches out to a known Google server, takes whatever it receives back, and sends it over to the analysis server. Presumably, the analysis server knows what that initial server should be returning. And so it's able to identify if there's something between the device and the internet. So, as I said, back when I looked at this specific version of Google Play SafetyNet, around about 2020, there were around about 55 different modules and variables being used across a bunch of different spectrums. Now, Google Play SafetyNet is actually being replaced, I want to say in 2024, so kind of how this is done might slightly change. But again, more of a window into the types of checks that are being performed on 90% of people here's devices. And again, that was just a look at the snet.jar file, rather than the actual computation that is happening to those variables. But we have around about 10 minutes or so left if anyone has any questions. But primarily what we've covered today is a look into attestation techniques, tamper detection techniques, root detection techniques that are happening on Android devices, the same techniques that software engineers or blue teamers need to put into place, and the same techniques that red teamers or malicious actors need to bypass. Once again, thanks to the organizers for having me here today. Thanks to all the volunteers, and thanks all for coming along. If you do have any questions, ask me now. You can find me afterwards. Or, yeah, go for it.
So, like, does the procedures change much between Android versions at all?
As in the SNet versions? Oh, definitely. Yeah. So, in fact, on another slide pack, I have a history of kind of all the different versions I've seen. And you can start to see them implement obfuscation. You can start to see them implement additional kind of different types of modules. So yeah, definitely over time, they've advanced how they're doing it. And as I said, 2024, 25, they're implementing a new version or a new system, which will be completely different again.
How fast do you see how fast do you see people developing the cracks and the routing techniques from say, a new version?
Yeah, so it definitely depends. So, one mitigation technique, you might use Frida or objection to get around some of these techniques. That method could be the same between versions. You might just hook a Google Play Safety Net call or API call in a third-party app, and that could be the same in multiple versions. It just depends. Yeah, go for it.
How the arms race is going between the anti-routing and the anti-anti-routing?
Yeah. So there was, when was it now? It was about 3 years ago. Google released hardware-based attestation, and that completely destroyed a lot of the anti-root detection. And Google are doing amazing. Like in the techniques that they're performing, it's really good stuff. I think with security as a whole, right? I think we'll always have that cat and mouse. And I think both sides are doing really good, in honesty. Yeah, go for it. Yes, so let me find the slide. So, there you go. So it's all a Google Play Services API. So there's a bunch of different Google Service APIs, things like maps and stuff like that are all based in their API. And one of their APIs is this Attestation framework, and these are all different types of APIs as well, all based in Google Play Services. Great. Yep. Sorry, I think I missed the start. What did you say? Sure. Mm-hmm. Sure. So Google have another service called Google Play Protect, which is responsible for basically daily scanning Android devices and identifying potential malware and other bits and pieces on those devices. So that is the component that's responsible for that side of security, and I've primarily focused on SNet. Any other questions? Yep, go for it.
What's preventing a routed device from tampering with that SNet jar and presumably
Yeah.
the
Yeah, so very similar to the cat and mouse question. It really just depends how much effort you put in as a vulnerability researcher or a reverse engineer. If you put enough time into finding those, or the SNet.jar file, or maybe man in the middling the SNet.jar file, things like that, it can definitely be done. Another bit of research I did was about seeing if I could replicate one for one that SNet.jar file, then put some alters in place and things like that. And it's also just about what control you have of the device. So, if you have root access on the device, you can then modify the system app of Google Play Services, and then you can put more things in place and things like that. But again, it's that kind of mouse, and also depends on what access you have and things like that. Okay, yeah, go for it. Mm-hmm. So both ecosystems are very different with iOS and Android. Primarily, I focus on Android. I've got a bit of experience in iOS. And things are a lot more locked down on iOS. So Apple control both the hardware and the software, while in Android kind of space, you only control the software for your vendor, and then someone else will control the hardware. So generally, it's a lot harder to jailbreak iOS compared to rooting Android. But yeah, swings and roundabouts. Great. Okay, I think that's all the questions. Great. Cheers, everyone. Thanks again for coming.